let's have a deeper look at homogeneous systems of equations. Remember, a homogeneous system of linear equations is a system of linear equations where all of the right-hand sides are equal to 0. If you have a homogeneous system of linear equations, so we'll solve this in the usual way by writing down its augmented matrix and then doing row reduction. So the augmented matrix looks like A11 through A1n, and then A down to AM1 over to AMN. And, you know, we would augment this with the right-hand side. That's the normal thing. But if all of your everything in your augmented column is 0, then all of the row operations that you do on this column will leave everything 0. So if you start with all zeros in this column, it's impossible to get anything but zeros when you're doing row operations. So for solving a homogeneous system, there's really no point in writing down this augmented column, because we know ahead of time, since we're starting with a homogeneous system, we know ahead of time that this augmentation column will always be nothing but zeros. So we don't even need to write it down. And we can work just with the unaugmented matrix for the system. So that's kind of nice. Another thing to notice about homogeneous systems is that there's one solution that you can always write down. If all of the right-hand sides are 0, then we can get a solution just by having nothing but zeros. So this is the x1 value up to the xn value. So this is always, having nothing but zeros for your x values is always a solution to a homogeneous system, because no matter what the a's are, if all the x values are 0, then everything on the left is 0, but everything on the right is 0 because it's a homogeneous system, and so this is a solution. So on the one hand, this is always a solution for a homogeneous system, but on the other hand, it's not very interesting as a solution, because this is always a solution to any homogeneous system. Since this is a genuine solution but not an interesting solution, we call this the trivial solution. And again, this is for homogeneous equations, for a homogeneous system. This is only a term we use for homogeneous systems. All right, so if you have a homogeneous system, you always have the trivial solution. There may be other solutions, and other solutions, those are really the interesting solutions. And other solutions, other than the trivial solution, we'll call non-trivial solutions. I know, it's a very creative terminology here. Okay, so when we solve a homogeneous system, really, we want to find out what are the non-trivial solutions. And we can solve a homogeneous system by just row reducing the matrix of coefficients. We don't need to worry about augmenting because there's nothing to augment with. All right, so let's look at an example. So let's solve this homogeneous system. Since it is homogeneous, we can just write down its matrix of coefficients, and we don't have to worry about writing down an augmented column. So -2, -4, 8, 3, 1, 3. And then we'll row reduce. So we'll start out by multiplying the first row by -1/2. So this leaves the second row alone. First row is now 1, 2, -4. And now we need to use this upper left 1 to get rid of the 3 below it. So we're going to do row 2 minus 3 times row 1. So first row is still 1, 2, -4. Second row is, so 3 minus 3 times 1 is 0. 1 minus 3 times 2 is -5. And 3 minus 3 times 4, so that's plus 12, that's 15. Okay. Now to get this into row echelon form, we need to make a 1 show up right here in the leading position in row 2. So we need to take row 2 and multiply by minus 1 over 5. So 1, 2, minus 4. And then 0, 1, minus 3. Since this column here, so this third column isn't going to have a leading 1 in it, and this is the column that corresponds to the variable z. So z is going to be a free variable, so the nicest way to write down a solution when you have a free variable is to go all the way to reduced row echelon form. So to do that, we need to use this leading one here to zero out the 2 that's above it. So when we do that, we're going to take row 1 and subtract 2 times row 2. So now row 2 doesn't change. It's still 0, 1, minus 3. But row 1 is now 1, 0, and then minus 4 plus 6, so that's 2. I hope I did that arithmetic right. Okay. So this, remember, this is the x column, this is the y column, this is the z column. So this corresponds to the system of equations x plus 2z equals 0 and y minus 3z equals 0. So z is a free variable. Remember, usually what we do is we, rather than using z as itself as a parameter, which actually is fine, but some people like to have a different variable for a parameter. So we'll say z, the free variable z is a parameter t, and then we can use this second equation to solve for y. So y is 3 times z, which is t, and then we can use this equation to solve for x. So x is minus 2 times z, but z is t. Okay. So this parameterizes the collection of solutions. There's kind of a nice way to express this. So writing it out individually, variable by variable like this is it's going to be a little bit cumbersome. So here's what we're going to do instead. We're going to sort of package everything up into a vector, but the way that we're going to write our vectors isn't, like this, like you might have done in other math classes or using angle brackets, or maybe in physics classes. What we're going to do is organize our vectors just as columns. So x is our first variable, so it'll go in the first column, so that's minus 2. Actually, let me write it like this. X is our first variable, so it's going to be in the first position in our column of variables, or in our vector of results here. And then y is next, and then z. And so x is minus 2t, y is 3t, and z is just t. All right. So one thing that we can do with this is this lets us realize that all of these coordinates all have t in them, so we could actually move t out front like this and write this as the vector minus 2, 3, 1 times a variable scalar t. So this sort of gives us a nice understanding, or a nice expression for what the collection of solutions looks like. It's just all multiples of this vector minus 2, 3, 1. All right, let's look at another example. So how about this system? So again, it's homogeneous, so we can write down a matrix for it. 4, minus 2, 1, minus 3, minus 1, 3, 1, minus 4, and then start row reducing. So let's switch row 1 and row 2. While we're at it, let's also, let's do things one at a time. Minus 1, 3, 1, minus 4, and then 4, minus 2, 1, minus 3. And then we'll do row 1, the negative of row 1, to to make this leading -1 a +1. So 1 minus 3 minus 1, 4, 4 minus 2, 1 minus 3. And then we're going to do row 2 minus 4 times row 1. So 1 minus 3 minus 1, 4. And then let's see, so 4 minus 4 times 1 is 0. Minus 2 times minus 4 times 3, so that's plus 12, so 10. And then 1 plus 4, so 5. Yes. And then minus 3 minus another 16. Yes. Minus 19. Okay. So now we need to take row 2 and divide by 10. 1 minus 3 minus 1, 4, 0, 1, 1/2, and negative 19 over 10. Okay, and then now we need to do row 1 plus 3 times row 2. So 1, 0, and then let's see, so then we're going to get -1 plus 3/2 is plus 1/2, and then 4 minus 3 times 19, so that's 30, 57. So negative 57 plus 40 is minus 17 tenths. 0, 1, 1/2, minus 19 over 10. Okay. All right, so some kind of messy numbers there. If I didn't get the arithmetic exactly right, you know, this is close enough to illustrate the point. So we have, so here's our X, Y, Z, and W columns. So, so X is, so right, this first equation is X plus 1/2 Z minus 17 over 10 W. So we can move the Z and the W term to the other side, and we get X equals minus 1/2 Z plus 17 over 10 W. For Y, right, again, we can take these two terms and move them to the other side. We get Y equals minus 1/2 Z plus 19 over 10 W. And Z is free, so we'll just give it a parameter name. How about S? And W is free, so let's give it a parameter. How about T? So our solutions are going to look like X, Y, Z, W. So this is, let's see, X is minus 1/2 Z plus 17 over 10 W. Y is minus 1/2 Z plus 19 over 10 W. I'm sorry, I keep writing Z and W. We gave these things parameter names, so let's use those. S instead of Z and T instead of W. Z is just S, W is just T. Okay. But we can do better than this, right? If you look at each part of this vector, it's a sum of two pieces, a part with S and a part with T. So we can split those parts, we can split those pieces apart. So the pieces with S are minus 1/2 S, minus 1/2 S, S, and then 0, right? Because there's a sort of a hidden plus 0 down here. And then the part with T is 17 over 10 T, 19 over 10 T, and then right there's a plus 0 right here, so the Z coordinate has a 0, and then just T. But splitting it up this way, now every coordinate in this first vector has an S in it, so we can move that S outside. So this is S times the vector 1/2, minus 1/2, minus 1/2, 1, 0. And then the second piece, we can move that t outside. So t, scalar product with the vector 17 over 10, 19 over 10, 0, 1. All right. So you can see that solving a homogeneous equation in this way and then parameterizing the solution like this should always let us express these solutions as some vectors, but with these free parameters in front. Okay.